Believe it or not, we are almost done with this chapter, this unit on stoichiometry, and really just think about everything that you can do now that you couldn't do just a few weeks ago. By this point, you at least should be able to take massive reactants and turn them into massive products. You can find the percent composition of a known compound and use percent compositions of unknown compounds to figure out their molecular formula. It's actually quite a bit of work that you can do now, taking things into moles, out of moles. There's just one little bit more that we have to do, and then we are done. We can start reviewing and taking the test. And that is regarding limiting reactants. And then one more little thing that's nice and easy actually, percent yield. Okay, now the concept of a limiting reactant essentially just asks which of the reactants that we have is going to limit how far the reaction goes. You may be wondering why I have VeggieTales cheeseburger song here, and well, it's to make a little point. Let's say that you're making a cheeseburger. What are you going to need? So think just a minute about some things you're going to need if you're going to make a cheeseburger. Well, at bare minimum, the list that I come up with is going to be you're going to need buns. You're going to need 2 buns per cheeseburger because you need a top and a bottom bun. You're going to need the patty. You're going to need a piece of cheese, and because burgers can be a bit dry, you're going to need some ketchup. So let's say 1 tablespoon ketchup. You may come up with different lists. We can play around with this in class a bit too. Now let's say you have the following ingredients: 10 buns, 8 hamburger patties, 8 pieces of cheese, and a whole bottle of ketchup, 50 tablespoons. How many burgers can you make with this? Well, we can definitely make 8 because we've got 8 patties and 8 pieces of cheese. We can make a whole bunch because we've got enough ketchup to make, let's see, 50 cheeseburgers. But how many buns do we have? Well, we only have 10 buns. And on top of that, we need 2 buns to make a burger. So divide 10 by 2 and you get 5. You can actually only make 5 cheeseburgers. Even though you have extra stuff left over, you've got one thing that limits how many we can make. And that's really as complicated as this gets for limiting reactants in chemistry. But in chemistry, we're not talking about these buns, patties, pieces of cheese. We're talking about compounds and chemicals. And since this is stoichiometry, we're not going to be talking about numbers like buns and patties and pieces. We're going to convert it all into, that's right, moles. Moles. Okay, let's try a problem here. To produce ammonia gas, that's NH3, a reaction must occur between hydrogen gas and nitrogen gas. Let's say that you start off with 20 grams of hydrogen gas and 20 grams of nitrogen gas. What is the limiting reactant? Go ahead and write that down for just a minute. See if you can do the problem. You might be able to do it even without my help, but go ahead and write and balance the reaction at least. All right, we should have something like this then. Nitrogen gas, 3 moles of hydrogen gas, gives us 2 moles of ammonia gas. Okay, great. Well, the next step then is going to be figuring out which of these is the limiting reactant. Which of the 2 reactants do we have the least amount of? Okay, well, let's do just a little bit of math here. Now, what did we have to start with? Well, I said you had 20 grams of each of them. So 20 grams here. And we wanted it to be not in grams, but always moles if we're going to compare. So if this is nitrogen that we're talking about, then we've got to look up the mass of 2 nitrogens. So that will give us 28.014 grams of nitrogen is going to be 1 mole of nitrogen. Cancel, cancel. We're left with moles of nitrogen, so it's set up correctly. Plug it into the calculator. Do 0.7139 moles of nitrogen. Okay, so a little bit less than a mole. Now do the exact same process for the hydrogen. Okay, and if you've done that, you should see that since hydrogen actually weighs way less than nitrogen, we've actually got a great many number of moles more of hydrogen than we do of nitrogen. One more thing to check. Going by our equation up here, we need 3 times as much hydrogen as we do of nitrogen. Well, let's take a look here. Is this at least 3 times more than this? Sure it is. It's looks like it's a great deal more. What is that? 10 or 12 times more? Plenty, plenty. That means that this is the one that we have the leftover of, which means that this one here is going to be what limits it. Nitrogen, the 20 grams nitrogen gas limits how far our reaction can go. It is the limiting reactant. Okay, let's take this a step further then. Let's take this one more step further, because now that we know which one's going to limit the reaction, we can use this for all sorts of stuff. Like what? Like what could we use it for? Well, we could use it to find out how much ammonia gas we can make at the end. We should be able to do that at this point, right? That's just going to be a simple mass-mass conversion. And in fact, we've already done the first step. Since we've already taken the mass of nitrogen and put it into moles of nitrogen, the rest of this should be a snap, shouldn't it? Let's do that then. From the previous problem, taken to the point where we've gone so far, how many grams of ammonia gas will the reaction make? Take just a minute, do that. Okay then, so we've got our 0.7139 moles of nitrogen down here. Okay, but we're not interested in nitrogen, we're interested in ammonia. So our balanced equation tells us that in every 1 mole of nitrogen gas that we have, we'll be able to make 2 moles of ammonia. Okay, good, good. That's going to cancel, so we're on the right track, but we don't want moles of ammonia. We're going to want grams of ammonia, so in 1 mole of ammonia, let's see, we've got, 3 hydrogens, and we've got 1 nitrogen. Should give us something like, what, 17.031 grams of ammonia, depending on how you round it, of course. Moles cancel out, and then we just multiply, multiply, multiply. Let's see, that times 2 times 0.7139 should give you something like 24.316, or I guess with 4 significant pit figures, 24.32 grams of ammonia. That's how much we make. That's how much we're going to make. How about that? Just one more thing that I want to do, and then again, that will be it for the calculations for this unit. And in fact, most of the calculations for the rest of the year. This chapter does contain the bulk of the calculations. We'll still be doing calculations in other chapters, but they'll be exactly the same as these. Okay, percent yield. Now, percent yield basically is just going to take into account the theoretical yield, which is how much of the product could you make? How much does the equation tell you you will make? And comparing that to the actual. How much did you really make? How much did you really make? Because nothing in life is 100%. There's always going to be some inefficiency. There's always going to be some waste. So the equation for that then is just going to be a nice simple actual divided by the theoretical multiplied by 100%. So let's say you only made 15 grams of ammonia instead of 24.32. What is your percent yield? Go ahead and do that problem. I'm not even going to show you. This is it's percent. You're going to take actual divided by theoretical multiply by 100%. Do that real. And you probably came up with 62%. Wow, 62%. It's not very high. Where could the extras have gone to? Where could all of that extra amount gone to? Well, it is possible that our apparatus had some sort of leak in it. Surely that could have released some of the ammonia into the air, and we weren't able to capture it. But there also is something called equilibrium, which we'll get into later, which basically says that not all the reactants are going to be made into products. There's going to be some point where it actually stops. That's another chapter for another day. Percent yield's the last thing we really have to worry about in this chapter. Great job. See you in class.